All right. So, hi everyone. Welcome to the March LRD Econ technical call. Today we have our guest presenter, Richard Nugent. He is here with us from HEC, and he's going to be talking with us about the current version, the latest version, I should say, of FDA 2.0. So I'm going to give you the floor, Richard, to introduce yourself, give a little bit of background context of who you are, and then go ahead and delve into the presentation. It's being recorded, and we'll be sure to share this broadly. So with that, the floor is yours. Thank you.
Thank you, Dean. I am so excited to be here and talk to you guys about 2.0. Right, so my name is Richard Nugent. I am an economist and the lead developer of HEC-FDA for HEC. That's maybe half of my job. Do all kinds of cool things in addition to that for HEC, but FDA is the main gig. I joined the Corps of Engineers in 2019 out of grad school. I finished my PhD in economics at the City University of New York Graduate Center. New York District picked me up in June 2019, and HEC grabbed me about a year and a half later. So I've been with HEC since, 3.5 years. Time flies. And so I know a lot of names in the audience, but there are quite a few I don't. Those I don't know, I'm always happy to make new friends. And so if things come up with economics or FDA, whatever, I like hearing from folks, so don't hesitate to shoot me an email ever. And those who are on the call who know me can attest that that is my favorite part of the job. So don't hesitate to reach out to me if anything comes up ever. All right, so HEC-FDA version 2.0, the software is done. We're not certified yet. So we're not using 2.0 on feasibility studies just yet. You can think about how to organize yourself for transitioning, but we don't have specific transition guidance in place yet, and it's not certified. So we're still using 1.4.3, but it's a great time to start thinking about moving to 2.0 and start working on all of the training that we have available. So that's the objective here today is to start familiarizing ourselves with this software as we work through our last few pieces of certification. So I'm gonna do a quick introduction to the team. Oh gosh, and I may not have updated that slide. Our team grows all the time because we constantly have new contributors. We'll do a quick primer on FDA. We've looked at the status. We'll look at major new capabilities, computational changes, differences in results, workflow changes, study conversions, and then I'm just going to walk through the user interface. So there's a whole lot of people who have contributed to getting 2.0 out, to include my boss, Leah Adams, Rebecca Augustine in New York, Brennan Beam, who's a teammate at HEC, Taylor Bolt out in Omaha, Will Lehman at HEC, Jordan Lucas, at HEC, Julia Slaughter. So that's a typo. Jordan Lucas is at St. Louis District, and Julia Slaughter at HEC. And we've also had some DA interns coming and contributing as well. Will Schaefer from Philly, and we had Andrea Demu and Hastings Merrick come from the hydro production economics team, hydroelectricity production, something like that. Something that most of us economists don't get exposed to, which was cool. So this is a real big team effort. Now what is HEC-FDA? This is the Corps of Engineers primary and at the moment only certified FRM decision support tool, which is a software that is developed by and maintained by economists for economists, right? So this is our inland and at times coastal flood risk management or flood risk assessment tool. This is how we calculate benefits. So what happens in the software is that we bring together hydrologic, hydraulic, geotechnical, and economic modeling together to get a picture of risk, right? Risk is a function of broadly probability and consequences, where probability is a function of the hazard and the performance, hazard being the logic and hydraulic conditions and the performance being the geotechnical conditions. And we bring that together with the consequences, which comes from the economic analysis. And HEC-FDA is going to compute expected annual damage, which is our risk estimate for a given analysis year and project conditions, such as the without project condition or alternative 2. EAD is specific to a base year, and then we bring EAD in the base year and EAD in the most likely future together to calculate average annual equivalent damage. HEC-FDA also performs risk assessment consistent with the methods described in Engineering Manual 1110-2-1619 and produces all of the results that are required for compliance with Engineering Regulation 1105-2-101. So this is the tool that you need for your FRM study. In the last 5 years, HEC-FDA has supported decisions on 24 chiefs reports that in total recommended $15 billion in FRM capital investment. So I'm only looking at the FRM studies, not the coastal studies that used FDA. So you're getting a conservative estimate of how important the software is. Those 24 chief reports in total documented about $1.8 billion in average annual equivalent FRM net benefits. So that's $1.8 billion of benefits every year, right? That's the constant stream that is being the decision to invest is being supported by this software, and we're getting a lot out of it. So this is it's a really important piece of software for the agency. Now, the algorithm in HEC-FDA is well illustrated by the 4 plots you see on the left-hand side of this slide. And I hope many are familiar with these 4 plots because we show them all the time. We can use these 4 plots to illustrate how we calculate risk. So risk is a function of the hazard, the performance, and the consequences. The hazard reflects the hydrologic and the hydraulic conditions. How much water is there and how high is it? Performance reflects whether there's a levee and how that levee responds to the hazard. What is the chance of the levee failing at a given stage? Or you can look at the geotechnical or the system response curve alternatively as the probability distribution of failure stages. We bring the hazard and the performance together with the consequences. How bad is damage going to be for different magnitudes of the hazard? Those 3 pieces are brought into HEC-FDA as summary relationships, right? A relationship between probability and discharge, a relationship between discharge and stage, a relationship between stage and damage, and relating those 3 together, we can get a relationship between damage and probability of exceedance, right? So the top right-hand side plot is just a cumulative distribution function of the hazard. And we transform the hazard into dollars so that we get a cumulative distribution function of damage in dollars that we integrate to calculate the expected value of that cumulative distribution function of damage. That expected value of the cumulative distribution function of damage, which is also called the damage exceedance probability function, is expected annual damage, our main measure of risk. Okay, so that's FDA in a nutshell. And on the right-hand side, I've got a screenshot of the scenario editor in HEC-FDA version 2.0, which is where you will bring together all of this data that we've plotted on the left-hand side, the hazard, the performance, the consequences. This is where you're going to select which pieces you need to calculate EAD for that specific analysis year and project condition. And a very cool thing about 2.0, a new thing in the software, is that you can visualize the 4 plots. You can actually graph the 4 plots in the software, and and that's really, really important because there's often a problem of lack of overlap across these relationships, right? So you may be familiar with the idea that FDA will not extrapolate the stage discharge function. And what we're saying is that if the discharges in the stage discharge function, the highest discharge is going to be quite a bit lower than the highest discharge in the flow exceedance probability function, then you truncate the probability function, right? And so using these 4 plots, you can see how well you are getting lined up across those functions so that you are able to basically transform, you want to transform the entire cumulative distribution function of the hazard to a cumulative distribution function of damage. But if parts of your transform are missing, then you can't transform your entire cumulative distribution function of the hazard, and it gets truncated. When you truncate that because you don't have good overlap, then you bias your EAD estimate. And so using these plots, we're encouraging you to take a look at how well you're actually transforming that entire distribution of the hazard into a distribution of damage. And if there's poor overlap, so you can see, for example, we can account for a lot more stages in stage damage than we could in the stage discharge. So it's those, we're not going to be calculating damage for those stages because, but does that matter? Well, we need to look at whether there's good discharge overlap, which there appears to be, right? We've got pretty good overlap for the cumulative distribution function of the hazard, though we are missing the top end, right? So we're going to be truncating the top end of the hazard curve there, and that's going to truncate the top end of the damage cumulative distribution function and bias the EAD estimate downward. All right, so this is the FDA in a nutshell, and a really cool new feature that's going to help us do better at fully describing the distribution of damage and giving a better estimate of EAD. All right, so let's look at major new capabilities. The biggest major new capability here is the ability to process geospatial data, right? So that means that HEC-FDA can read, understand, analyze 2D hydraulic modeling without the need to pre-process it and put it into a flat file, a water surface profile flat file. We can take the native output for HEC-RAS, which is HDF, and plug it right into FDA, right? So FDA can now understand depth grids, which is typically how we think about geospatial hydraulic modeling. Though in FDA we're going to discourage depths, we're only going to explicitly handle water surface elevation, right? So we want to know what the elevation of the water is, and we are encouraging using the HDF output instead of water surface elevation grids, because the HDF is a much more convenient way to transfer the data. The grids are can be large. So we're going out with this idea that a river is a straight line, and that flooding goes down that line. We are in with the idea that we can visualize and analyze the water at specific locations instead of having to do this reach-based and interpolation-based approach. We have new cool ways to report risk. So we are now displaying the distribution of EAD, the entire distribution. We're still reporting the quartiles. In FDA 1.4.3, we referred to the quartiles as there's a table probability that damage exceeds indicated value or something. I don't know. It's really wordy. Sometimes we like to figure out the most complicated way we can say something. It's just the quartile, right? So the what we display for the distribution of damage to be consistent with 101 is the quartiles. The first, second, and third, along with the mean. The second is the median, right? That's what we need to display. That's what we're calling it, quartiles. And you can see the entire distribution here. This is the cumulative distribution function of EAD. We're also displaying, as you would expect, EAD, mean EAD for the different damage categories. All right. Let's see, where did I go wrong? There we go. System performance. A couple of cool new features here. We are displaying the distribution of AEP. And that's what you see in this histogram here. So the performance that you would report from FDA 1.4.3 and what you see in Table 1 of Engineering Regulation 1105-2-101 includes the mean and median AEP, long-term exceedance probability at 10, 30, and 50 years, and conditional non-exceedance probability for these 6 frequencies, 0.1, 0.04, 0.02, 0.01, 0.004, and 0.002. But 101 also tells you that you need to describe assurance of AEP, not just assurance of stage, right? Assurance of stage or assurance of threshold is what we also refer to as conditional non-exceedance probability, and that's going to tell you, describe the distribution of stages. But we also want to think about the distribution of AEPs. There's a line in special guidance, I think it's paragraph 8J something. You need to be able to communicate the AEP that passes with 90% assurance. And that means that you need to be able to describe the assurance of AEP. And in 1.4.3, you had to go through text files to get at the assurance of AEP, but you don't have to do that anymore. Because assurance of AEP is now here in the standard reporting, and in the summary report, we're going to even report that specific AEP that has 90% assurance, so that you don't have to go and try to interpolate or calculate it. We're going to report that in the summary results. Other new capabilities, so we can do a uniform distribution now, in addition to normal, triangular, log normal. We are including uncertainty about content other than vehicle value. So we used to only be able to include, or in 1.4.3, you can only do uncertainty about a content to structure value ratio or other to structure value ratio. But if you go straight to content value instead of using the ratio, you couldn't include uncertainty, and now you can do that in 2.0. And we've got the view of the summary relationships 4-plot diagram. There's a whole bunch of new stuff that just came about because we have a new let's say architecture. Were built on new technology that made a whole bunch of things capable. And so you can find all those changes. There are changes in the release notes, and we also describe differences in our user documentation. But I've highlighted, I think, the biggest ones here that relate to the user experience. Then there are computational changes. And I'm gonna, yeah, okay. So let's talk about the computational changes. Bear with me. So there, we did our best to not make any changes except where we felt compelled, or except where we were really compelled to make the change. And this is what you're seeing here is an illustration of one of those changes. HEC-FDA version 1.4.3 implemented a procedure for evaluating the uncertainty about a flow frequency function using a method that was consistent with the guidelines of USGS Bulletin 17B. And USGS Bulletin 17B has since been replaced by USGS Bulletin 17C, which gives us new guidelines for incorporating the uncertainty or describing the uncertainty around a flow frequency function. Those new guidelines allow us to, or describe a way to incorporate uncertainty and skew in addition to uncertainty and mean and standard deviation about that flow frequency function, right? So our analytical flow frequency functions are described using log Pearson type 3 distributions, which it's a special version of a normal distribution. The log Pearson type 3 distribution is parameterized using a mean, a standard deviation, and a skew. That log Pearson type 3 distribution describes the natural variability of flow, right? The variability of peak flow in a given year. But then we have that knowledge uncertainty, which is, do we know the true mean, standard deviation, and skew of that log Pearson type 3 distribution for that particular river, right? Do we know the true mean, standard deviation, and skew of flows for the Des Plaines? We could estimate it, but we don't really know it. And so we need to incorporate our knowledge uncertainty about the mean, standard deviation, and skew. And in 1.4.3, we didn't have a way to incorporate uncertainty and skew, so we only varied the mean and standard deviation, and skew was kept constant. And so you can imagine that we were ignoring part of the uncertainty when we use these analytical flow frequency functions. And now that we're bringing that additional uncertainty in, we're going to have wider or greater uncertainty about our flow frequency functions. And so in this illustration, we have a plot where annual maximum flow is on the y-axis and annual exceedance probability is on the x-axis. The LP3 input, or the estimated mean, standard deviation, and skew, is given by the black line. And then we use have compared the different methods to calculate the bounds, the fifth percentile, 95th percentile of flows at each of these AEPs using our two different approaches, the 1.4.3 and 2.0. And you can see that 2.0 is giving you wider bounds for flow about a given exceedance probability. And that is the effect of including additional uncertainty, that additional uncertainty that is attributable to uncertainty and skew. Now, this is only going to come into play if you're using an analytical flow frequency function, which is not common. We'd like to see it more often when it's possible. I understand, typically teams are relying on graphical frequency for any number of constraints. But this is, if you can describe the hydrology using log Pearson type 3, it's highly encouraged. Okay, other changes. So we made other computational changes where it was really important. We made a fix to sampling triangular distributions. There was a bug in 1.4.3 where triangular distributions weren't being sampled correctly all the time. I'm going to skip over number 2 and come back to that. So aggregation stages are now being identified from summary relationships. In 1.4.3, when we looked at which aggregation stages to use for the stage damage calculation, we put those stages together using a combination of the summary relationships and the water surface profiles, which exposed us to inconsistencies. And so now we're just going to use the summary relationships to figure out what the stages are at the index location at which we're going to calculate damage. And that means that you need summary relationships to calculate stage damage. You can no longer just use water surface profiles. You need to specify your flow frequency and stage flow functions. Our assumed water surface elevation structures are now identified geospatially instead of being interpolated based on water surface profile data. And we have a barely dry adjustment added. That barely dry adjustment means that if a structure is not wet for a given AEP in the hydraulic data set, but then it's wet in the next one, we're going to set the depth to -2. And that's going to help us interpolate between those two AEPs. All right, now let me go back to number 2. The distribution and damage for a given stage is represented empirically. This is turning out to be a big one. It's here in the small list because we are tracking LP3 as being the big one, but this is turning out to be the big one. And I'm going to tell you how much I know about it today, which is only a complete picture. We have more investigation to do. So what is this change about? Well, HEC-FDA version 1.4.3, when we are calculating stage damage with uncertainty, right, we calculate a sample of 5,000 damages for a given stage when we're calculating stage damage with uncertainty, the aggregated stage damage with uncertainty. And HEC-FDA version 1.4.3 is going to take that sample of 5,000 damages and calculate the mean and standard deviation, fit a normal distribution to that sample, and then throw the sample out. We keep the normal distribution in the database, and we analyze that normal distribution of damage for a given stage in our calculation of EAD. The problem is that sample of 5,000 damages can look very different from normal. And when you fit a normal distribution to something that doesn't look like normal, you're causing bias. And we're seeing anecdotally that bias can be significant. So this change is going to come into play when you recompute stage damage, and there will be an impact to EAD. This is a step forward, right? We are making technological progress here. Our team saw that making that assumption. I mean, I was grad school. We're hammered over the head about making distributional assumptions. It's something that you can avoid. It's really these are like principles, and so it makes perfect sense to avoid making a distributional assumption if you can, and we figured out how to. Right, so we have a statistical library with tools that allow us to evaluate empirical distributions explicitly. In the same way, with all the same functionality, so the empirical distribution has all the same functionality that the normal distribution does. So it's a perfect substitute in that it has all the same capability, but it's a better substitute in that our distributions are more effectively representing what the shape of the distribution of damage actually is. And so we're not biasing the result by making that bad distributional assumption. You can please look out for more information on this. The development team and the review team and the steering committee are going to be working together to set us up with a better understanding of how this affects EAD and what we want to do with that. So please look out for more information on that. So I just talked to you about, there are changes in EADs. It could be affected, and it's true. But I do want to spend a little bit of time thinking about our tests. So HEC-FDA version 2.0 it's certainly one of the most well-tested risk assessment software you're going to find. Okay, we have more than 400 automated tests that confirm that all of our calculations are taking place. And every single time that we make a change, those 400 tests are run. Right, so this is a very well-tested piece of software, and it's also open source. And all of those tests are available to you, as well as the test data. So this software, you can go to GitHub, you can look at all of our tests and confirm on paper that the calculations that we're making in the software make sense. And if you're interested in looking at that, please reach out to me and I'll walk you. I can point you out to it. But I just want to make this point that these differences may take place, but we have proven through all of this testing and public documentation of that testing that our outcomes are valid. A lot of our tests do look at 1.4.3 as a benchmark, and we're seeing results within 5% if we use stage damage calculated in 1.4.3. But when we don't, remember, then we bring in this new distributional assumption or ability to avoid the distributional assumption, and then results are not within 5%. I have an example of one of those tests here. So this is one of our unit tests, and you can see the first few lines. I have some XML comments where the study data for the below test can be found at HTTPS, so on and so forth. So that's a link to an Excel file where I have replicated the test that is taking place in the code and come up with the expected value. And I confirm that the expected value in my Excel sheet matches the expected value from the my software test. And what you can see is the last line, I have an assert.true, relative difference is less than 0.016. So for this test, the value that I calculated in Excel is less than 1.6% different from the value calculated in the software. And we have 400 of these, and many of these have many different cases. So this software is really well tested, and publicly available, so you can go and get nerdy, get in the weeds, and look at how we're doing all this testing, and maybe even help us improve, which is really the objective of open source. We want to be engaged with the field in development. Okay. A couple of changes in workflow. All 1D data sets are now required to be in 2D. Okay, so what does that mean? HEC-FDA version 2.0 does not have the capability to read a 1D water surface profile flat file. Right, the flat file gave you a list of river stations and a list of water surface elevations, and the houses were assumed to be all along the river, right? Though at their different elevations, and we interpolated the stage at that water surface elevation based on this line of stations. But now, we know that the world is not a line, and so the data sets can't be. The hazard data and the structure data can't be based on lines. It needs to be based on a map. So we need terrain in geospatial format. We need impact area sets in geospatial format. We need the hydraulic data set in geospatial format. And we need the structure inventory in geospatial format, because all of these things have a geospatial component to them. We have moved to an object-oriented software program. Object-oriented, so we're using C#, which is the .NET programming language, which is one of the most advanced programming languages out there right now, and is very well supported. It's Microsoft's programming language. But moving to object-oriented has actually relieved us of some constraints that were imposed by functional programming and resulted in frictions for the user. And one of those good examples is the structure module. In HEC-FDA version 1.4.3, if you wanted to use your inventory differently for different alternatives, then you needed to chop up that inventory into different modules. And 1.4.3 would try to look at, okay, which indices of the inventory am I going to use for which plan, right? So it was a data frame, and we chopped up that data frame differently for different plans. But this world of data frames and functional programming, that's old school. In an object-oriented world, we can treat entire inventories as entire objects. So you'll have a without project condition inventory, and you'll have an inventory for the with project condition, say the quote-unquote 100-year non-structural plan. Colloquial, 100-year non-structural plan, colloquial. You may have another inventory for non-structural actions that are even more aggressive, or another inventory for non-structural actions that are a little less aggressive, right? So we have entire objects. And that makes, I think that's going to make plan formulation a little bit easier. Another result of moving to an object-oriented programming, and a result of having to develop this really quickly, is that we now have in the workflow something called a scenario, something called an alternative, and something called an alternative comparison report, which are these three objects that you're going to be creating. The scenario is a collection of all of the components of the risk equation, right? So you'll collect your hazard data, your performance data, your economics data, and tell the software to compute EAD and performance for that collection. And that's that scenario. You'll have one scenario for your base year, one scenario for your future year, and you'll connect those two for an alternative. For that alternative, you'll be able to calculate average annual equivalent damage, right? Because to be able, you need to take into account the time value of money in order to compare damage reduced to cost. So once you have your alternatives, you'll have your without project condition alternative, which will consist of base year and future year without project condition. You'll have your with project alternatives, which will consist of your with project base year and future year EADs, and calculated into average annual equivalent damage. You'll have your whole array of alternatives, and you'll bring those into alternative comparison report. You'll create that report, and that'll be a comparison of the without project condition to all the with project conditions. So you're creating these three objects. In the future, there's probably, there's certainly going to be ways to make that faster, but our need to get a piece of software to you has meant focusing on critical functionality. Okay, so another fun thing with object-oriented software meant that we can accommodate multiple sets of index points. Now, index points are not actually going to be required in HEC-FDA version 1.2.0. But if you do want to use them, then and need multiple sets because certain index points are better for certain alternatives than others, then you can. So I can talk a minute about not needing an index point in 2.0. The concept of an index point is not going away. It's just that it is not need in 2.0 does not need to keep track of it. The FDA does not need to keep track of the index point. When you bring in your summary relationships, your flow frequency function and your stage flow function, those functions should be identified at the index point. We use those functions in the stage damage calculation to identify the stages at which we're going to calculate damage. So inherently, we use the index point in the stage damage calculation by looking at the summary relationships for the stages at which we'll calculate damage, and those summary relationships have been pulled from the index point by the engineers. In 1.4.3, we needed the index point because when we calculated stage damage, we would look at what are the stages in the water surface profile at the index point, and what are the range of stages and the summary relationships for that reach. And we would combine that information, which is silly. And I'm not going to get into that now. But it's just that we don't need to keep track of an index point in FDA. The only time that you're going to need to use an index point is if you're going to retrieve graphical stage frequency functions from your hydraulic data set. And that's only in the case that you're using stage frequency functions and you cannot include flow in your model, right? So we want to include flow in our HEC-FDA studies as much as we can, because we know that uncertainty in flow is one of the greatest contributors to uncertainty in EAD. But sometimes it's hard to include flow in our HEC-FDA study because there is not a one-to-one relationship between peak flow and peak stage, such as situations where we have backwater or tidal influence. In that case, you have to go straight to stage frequency. And if you have to go straight to stage frequency, then you're probably going to retrieve graphical stage frequency functions from your hydraulics data set. And you can use the index points, an index point data set, which will be a point shape file, to tell the software at which locations in the hydraulic data set do you want to pull those stages. When you do that, you're still going to want to improve the frequency functions that you pulled, just as you did in 1.4.3, right? You're going to want to add additional coordinates, because 8 coordinates is a small number of points to linearly approximate a nonlinear function, especially when you are identifying only half of the function, right? So if you start at the 0.5, that's only half the function. We need to know what the other half looks like, and if there's damage for the 2 year, we're going to say that there's damage in the 1 year unless you tell us there's not, because we don't extrapolate. Anyway, so index points only helpful if you're going to use stage frequency, and we only go straight to stage frequency in certain situations. Otherwise, you don't need index points. They're not going to be helpful because you can't pull a flow frequency function from a hydraulics data set. Right? There's flow information in a 2D hydraulic modeling. So we're not going to use it. We don't need index points anymore. And I've walked through that. All right, so let's walk through some of the steps, and then I'm going to take a look at the software. Study conversion is not going to be quick and easy. There are going to be multiple steps because we are converting 1990s technology to 2020s technology, right? And so I want you to think about, as before you go and do this and get frustrated with me. No, you're going to get frustrated with me, and that's okay. But before you do, think about what would it take you to get the data that's on your floppy disk into the cloud? How many steps would that take? That's the problem you're facing, right? We're trying to get data on the floppy disk into the cloud. Converting 1.4.3 to 2.0 is the same problem, right? 1.4.3 is based on technology and that was supported by companies that don't exist anymore. So we got to get the data on the floppy disk into the cloud, and it's gonna a few steps. But I've been told that it's not too complicated. So what will you need to convert your 1.4.3 study? You'll need all of your 1.4.3 study data, and your 1.4.3 study data should include your aggregated stage damage functions. You'll also need an impact area polygon shapefile. And what you'll do is, in your 1.4.3 study, you'll need to open up the Econ Parm database and change the flag for the aggregated stage damage export to 1. You can open that database, the Econ Parm database, in like GIS software. And there's a tutorial among our user documentation on how to do that. You'll export that study data, including those stage damage functions. You'll create your impact area polygon shapefile, and you'll be prepared then to create your new 2.0 study. You'll import your 1.4.3 study data. You'll import that impact area set that you created, and then you're going to import the 1.4.3 study data again for your stage damage functions. And you have to import the stage damage functions after you import all of the rest of the study data, because we need to have the impact areas in memory first. We have to have the impact area set in memory first. Once you have imported those stage damage functions, your 1.4.3 stage damage functions, you can create your scenarios, right? So your scenarios, that's your collection of stage damage, flow frequency, stage flow for a given project condition and analysis year. You'll do that for all of your analysis years and project conditions. You can do that using a batch compute. That's a right click on the scenarios item in the menu, and we'll see that in a second. Once you've computed all scenarios, you create your alternatives relating your project condition specific scenarios for each analysis year together. You can view those summary results, and then you can create your alternative comparison report. You identify what is your without project alternative and select the with project alternatives for which you want to see a comparison, and you view those results. So this might take you, depending on how long it takes to create the impact area polygon shapefile, it shouldn't take you more than an hour. Though if you have a lot of alternatives or a lot of damage reaches, then step 7 could take a bit of time. And that is a pain point that we are tracking. Britt Corley has chewed me out on multiple occasions because of it. Okay, so what about a new study? So what are the new study data requirements? We need typical economics data, and for engineering, we need the summary relationships in the hydraulics data set. So for economics of planning, you need to identify the analysis years, the discount rate. You'll need to put together an impact area set polygon shape file. You need your occupancy types. The occupancy types can be provided in the exact same format, tab delimited format that 1.4.3 expects. And that is documented in the appendix of the 1.4.1 user's manual. Optionally, you can bring in a terrain data set. And I will want to change that actually to encouraged. We encourage you to bring in a terrain data set so that you can use the same terrain data set that was used for the hydraulic modeling to identify the ground elevations at the structures. That allows for some nice consistency. So the terrain data set should be the same terrain data that was used for the hydraulic modeling. Grab that terrain and grab the ground elevations for the structures using that terrain, and that's going to give you a better answer. What about engineering? Engineering, you need a hydraulics data set for each analysis year and project condition. You need flow frequency and stage flow functions for each project condition and analysis year. If there is not a one-to-one relationship between peak stage and peak flow, peak stage and peak flow, then you might just go straight to stage frequency. And then optionally, regulated, unregulated, if you're going to model some sort of detention or dam, or levee data, which would include the top elevation of the levee and the system response curve, where you identify the probability of levee failure at the different stages. Okay, so this is in essence the data that you need.
Hey,
and
Richard.
Yeah.
Can you, on the hydraulics data, you had said on a slide earlier something about 1D versus 2D, and like we can still use 1D hydraulics in here, or steady flow hydraulics also, right? Could you kind of confirm that?
Of course. Thanks, Kurt. Very good point. So we're not saying you can't use 1D hydraulic modeling. You absolutely can. But the 1D hydraulic modeling needs to be in geospatial format. And it is perfectly possible and feasible using HEC-RAS to export your 1D hydraulic modeling in geospatial format. So 1D is perfectly handled. It just needs to be in geospatial format, not in that water surface profile flat file. Thank you, Kurt, for helping me elaborate on that. Cool. All right. So we have our new study workflow, and then just looking at the software. The new study workflow is importing the data, and then you're doing the same, configuring scenarios, alternatives, and alternative comparison reports. Okay. So let's just go ahead and look at the software now, right? So this is HEC-FDA version 2.0. I have open a solution for one of our workshops. And you can see that this software looks relatively familiar. We're trying in the core to give a similar look and feel to a lot of our software programs. You've got the study tree on the left-hand side. On the right-hand side is where all the editor windows are going to open up, and one day there will be a map window there. So your first step when you open up the software, you're going to either create a new study or open a study. You can also import 1.4.3. This import button is going to create you a new study. Once you do that, you're going to want to specify the properties. Some properties that are important to look at are your discount rate, your analysis years. You've got that price index information, convergence criteria, that kind of stuff. Leave that alone unless you're doing sensitivity analysis and you need stuff to compute fast. One other really important thing that you need to specify is the project projection file. right? So this is going to be a huge headache for a lot of us. It's already been a headache in testing, and that's making sure that all of our geospatial data sets can talk to each other. And so it's going to help a lot to make sure before you even import those geospatial data sets that they all have the same coordinate reference system. Now, if they don't, give us a projection file and we're going to try to reproject on the fly. And it's pretty successful, but reprojecting on the fly is not perfect. And so that's going to be some data management that we're going to encourage before you start importing, is making sure that your data sets can speak to each other. Because if they have different coordinate reference systems, they're speaking different languages. And the software is not a language converter. We can try, but we don't have I don't know of any robust reprojection stuff on the fly. We'll constantly try to improve, but it's going to be really important for you guys to make sure that the data sets can speak to each other before you bring them in the software and ask them to talk to each other. So, and setting the projection file, that's a good backup. All right, so we got our properties. You're going to do things like right-click on the terrain and import your terrain if you want to. If you have that terrain to pull your ground elevations from, you need an impact area set. So you'll import an impact area set. You can only have one terrain and one impact area set. If you want index points, you can create new index points. You can have as many as you like. You'll import a hydraulics data set for each project condition and analysis year. You can either import unsteady HDF, which will consist of a folder of 8 subdirectories. You can import a steady HDF, which will consist of a folder of 8 HDFs, I believe. 1 HDF. It'll be 1 HDF. This is the steady HDF is a file explorer that selects 1 HDF. Unsteady, there's going to be 8 HDFs in 8 separate subdirectories. And then there's gridded data. The gridded data should be also in 8 separate subdirectories, each of which should have a VRT and a TIFF. The gridded data is much larger than the HDF, so it's not helpful for bringing between RAS and FDA, though the gridded data can be easier to troubleshoot. You'll need to bring in your frequency functions, whether that's flow frequency or stage frequency. Ideally, it's flow frequency. And if flow frequency, you'll need to specify whether you're going to use graphical or analytical. So let's look at creating a new frequency function. You're either going to do analytical or graphical. If it's graphical, it's flow or stage. And what you're looking at is this is the frequency function editor, which looks like most editors. You're going to see a table with a plot. And a very cool thing with this table, you can copy and paste. You can copy this data, paste it into Excel. You can copy data out of Excel and paste it into this table. Okay. So you need to specify all your frequency functions. You should have one frequency function for every impact area, project condition, analysis, year combination, because that frequency function is specific to those dimensions. If you're going to model a diversion or a dam, you may want to bring in a regulated transform function, and in which case you're going to have that function for the specific impact area that's being affected and in the specific analysis year and project's condition. You need your stage transform functions. So if you have flow in your HEC-FDA study, you need to bring in a stage discharge function, one for each analysis year, project condition, and impact area. It's typical to use a triangular distribution of stages at each discharge. And note that this data, if you have this 4 columns with the stages, the min, most likely, and max stages in Excel, you can copy those 4 columns, specify triangular, and then paste the data into here. Imagine that. Copy and paste. Ha! All right, so you've got a stage discharge, one for each impact area, project condition, analysis year. exterior interior functions, the use of these in the 2D world is very nuanced. If you want to use them, please call me so we can talk about it. Lateral structures, your levees, right? So your levees, you're going to have a name, a description, a top of levee elevation, and a system response curve. If you tell us default, then we assume that the probability of failure is 0 up to the top of levee elevation, and then after which the probability is 1. So we assume that your levee is perfect, and then there's certain failure upon overtopping, which is not a great assumption. So we want to do user defined if we can. Lateral structures, right. Note that you're not going to need to specify what impact area this is for. Because we're in this object-oriented world, when you go to specify your scenario, you're going to have a scenario for your specific impact area up, and in that editor, that's where you select this levee, and we'll take a look at that. You'll bring in your occupancy types, and again, you can import occupancy types from the same tab delimited format that is documented in the HEC-FDA version 1.4.1 user's manual in the appendix. Then you're going to import your structure inventories. This should be a shapefile, a point shapefile. And you're going to find that here. You go look for your point shapefile. Required attributes, either first floor elevation or ground elevation and foundation height. Ground elevation and foundation height is most common, and we are encouraging that you grab the ground elevation from the terrain file if you've imported that terrain file and you have the terrain file from your that was used in the hydraulics modeling. You'll specify which of the attributes in the shapefile correspond to the attributes we want in the database, and so I'll just show you a quick example here, right? So these are all of the attributes in the shapefile attribute table. You're going to want to specify, okay, which attribute in the attribute table of that shapefile corresponds to the structure ID. That's what we're doing here. You'll figure out which, make this concordination between the required attributes, and then if you have any optional, you'll click next. Yeah, you can't have duplicated structure IDs, and you can't have. We've got validation that's working. Let's see why my structure ID is not working. This is the hazard of a live demo. I don't know if that's an ID. All right, well, we're not gonna show you that. Anyways, so when we click next, you're gonna have a very similar workflow where you'll need to select the occupancy type name from your occupancy types file and assign it to the occupancy type name that we pulled from your structure inventory, and you'll click import. All right, so we've imported our data. Now we can start calculating stuff. And I see that we're 1 minute over. I'm gonna get through this in about 7 minutes. So if you can hang on, please hang on. And if you can't, we are recording. So aggregated stage damage, you're either going to import from that tab delimited text file, or you're going to compute. So if we want to create new stage damage functions, you can enter manually, and you'll enter manually if, remember 1.4.3, you could use direct dollar stage damage functions. This is how you're going to enter that using our manual stage damage. Otherwise, you're just going to compute. You'll specify the analysis here. This text box is for your documentation purposes. We're not keeping track of the analysis here, you are. You'll select which water surface elevations, which structures. You'll also select which frequency function, which stage discharge function. Right, so we need to know the water surface elevations tell us what is the water level at the structures. The structures tell us where the structures are and their attributes. Then the frequency function and stage discharge function tell us what the stages are at the index location. All right, and we'll compute. You'll do that for every single project condition and analysis here. And in this example, we've got 2 existing stage damage, and we've got non-structural. So base year, future year, base year, future year. Then you need to create all of your scenarios. Let's take a look at a scenario. The scenario, remember, this is where we collect all of our data for our risk compute, EAD, and performance. We're going to have we'll have a scenario data specific to each impact area, and you can see that these are the tabs for each impact area. For your scenario, you'll need to give it a good name, a good description, a good analysis year. These 3 text boxes are for your documentation purposes. You'll select your stage damage functions that correspond to this project's condition and analysis year. If you're modeling the non-failure scenario, you'll select this and include your stage damage functions, which reflect the non-failure scenario. I don't want to go into what the non-failure stuff now. If you're interested, please reach out to me or look out for the user documentation where we have described our ability to now calculate total risk, which is including failure and non-failure risk in the risk estimate. Good. So we've decided what our stage damage functions. We have the without base condition, which is existing stage damage for the base year. We need to specify what is the frequency relationship for the left bank, what is the stage discharge for the left bank. We're not doing regulated, unregulated because we don't have a dam. We're not going to put a lateral structure here because this is without project condition, so we don't have a levee there. We click that our scenario reflects without project condition because it does. We can preview compute and take a look at this. We'll specify both left bank and right bank, selecting our frequency relation, all of our summary relationships. We'll save and close. Once we make all of our selections, we can go to compute scenarios and do a compute batch. Once we finish that, we can view summary results and look at the EAD and performance results for all of the scenarios. Now, I want to point out one thing about describing the scenarios or configuring the scenarios is that sometimes you're going to need to identify the threshold stage, right? So recall that the threshold stage in an impact area that does not have a levee is defined as the stage at which 5% of the damage of the 1% event occurs. And that's for the without project condition. If in the with project condition we also don't have a levee, then we need to use the stage from the without project condition, right? So say that, God forbid, we're going to do some channelization. That channelization is going to have lower stages at the given frequencies, and so we're going to expect better performance. The way that we reflect that better performance is by using the same stage for the with project condition threshold that we used for the without project condition threshold. All right, so you'll need to go to, if you don't have a levee in this impact area, we're going to calculate the stage for you. But if it's the with project condition, you need to tell us what that stage is. And we can do that. You'll either right click and go view thresholds, or you can also, the same thing that you can do is go by looking at the performance. For the without project condition, you'll see that the threshold stage is documented here, additional exterior stage. I didn't show you this view thresholds because that report is being worked on right now. All right, so it's important. Decide whether your scenario reflects without project conditions or not. If you choose a levee, if you have a levee for that specific impact area scenario, then the threshold stage is defined by the threshold is defined by the levee, and we don't need to worry about 5% of 1% event and whether it's the without project or with project. Okay, so all of this data needs to be specified. You can also add additional thresholds, and this is going to be very helpful for the teams that like to use. So I have this window over here for the teams that like to use RAS to model the effect of the levee, right? So if all of your structural measures are included in your hydraulics data set, then your project performance statistics don't make sense, right? Well, in 2.0, you can add a threshold, give us the stage of the levee, and we can calculate performance metrics that make sense. We don't have the ability to include system performance just yet if you're including your structural measures in your hydraulics dataset, but that is perfectly possible. And if a team needs it, then let us know and we can prioritize it. All right, so we have specified for each impact area our risk equation, right? We selected the hazard data. We selected the performance data. We selected the economics data. We specified our performance target. And we did that for all the project conditions and analysis years. So we have one scenario for each project condition analysis year. So we have one mean EAD and mean AEP for each project condition analysis year. Now we're ready to calculate average annual equivalent damage, right? Because we've got a base year EAD, we've got a future year EAD. We want to take into account the time value of money and calculate average annual equivalent damage, and we're going to do that with an alternative. You do that by deciding, okay, what's your base year scenario, your future year scenario, give us your years. These years are used in the calculation, okay? These are not just documentation. These years we use in calculating average annual equivalent damage. So it's really important that these are correct. So specifying an alternative is easy peasy, right? You give us a name, description, what's the base year, what's the future year, scenarios, what's the base year, what's the future year, save and close. And then you can do the same thing. You can view alternative summary results, and we're going to give you the alternative summary results for all of the alternatives that you specified. Let's take a look. We'll take a look at results in just a minute. Finally, create a new alternative comparison report so that you can look at what damages reduced are. Here you're going to compare without project damage to all the with project damage, right? And you can add additional comparisons. You can remove comparisons. Say that you only want to look at get results for 3, and the other 4 are outdated or something. You specify which comparisons you want to use. Okay. Now let's take a look at results. So you've come up with all of your comparisons. I'm going to look at summary results, and then we're going to call it quits. So let's view the summary results for scenarios. We're going to give you total expected annual damage. That's total over all of the damage categories and asset categories. Asset categories being structure, content, other, vehicle. So you've got mean expected annual damage for the base year for without base, right? Without project condition base year 2024, and we're giving you those quartiles. In 1.4.3, you would have seen some nonsense language, the probability that damage exceeds the indicated value, whatever. It's just the first quartile, second quartile, third quartile. We also give you mean expected annual damage by damage category for each project condition analysis year, so that's for each scenario. Let's move down. Looking at this table, this is table 1 in Engineering Regulation 1105-2-101. Right, you've got your mean and median annual exceedance probability, your long-term exceedance probability for 10, 30, and 50 years, and your assurance of threshold for those events of interest. But then we also need assurance of AEP, right? Engineering Regulation 1105-2-101 tells us that we need to communicate the AEP that has 90% assurance. And that's what you're seeing in this table, where we report the AEP that has 90% assurance, as well as the assurance of AEP, and the assurance of AEP being really important for NFIP evaluations. Okay, so that's the results for scenarios, right? Scenarios are EAD and performance. They're specific to a project condition and a base year or an analysis year. Then once we've taken into account time value of money, we can view the results. Let's just go ahead and take a look at all of the results. You're mad at me. It's mad at me because I changed some stuff. So let's just look at these results. For a specific alternative, we're looking at damage with uncertainty. This is average annual equivalent damage with uncertainty, right? So, this is the distribution of average annual equivalent damage over the period of analysis, and we're also reporting the quartiles, and you can look at by impact area and by damage category for that alternative. But the most interesting, where we're going to calculate benefits, you're going to look at benefits is the alternative comparison report. So now we are evaluating all of the alternatives data to come up with either the difference in EAD or the difference in AAEQ. The difference in AAEQ is what you need to compare benefits to costs. And here we have the damage distribution of average annual equivalent damage between the levy-only plan and the without project condition, showing you damage with uncertainty. The mean damage reduced is 8,000. And we have a distribution that lies somewhere below 0 to well above 0. And you can look at a summary result for the table that's going to be real helpful for your feasibility studies. You can just copy and paste this stuff out. We've got your without project alternative let's see, what's the one that we really want? AEEQ, right? Because AEEQ is what we need to compare to cost. So that's this bottom table without project alternative, with project, without project alternative, without project damage, with project alternative, with project damage, the difference of those means, and then the quartiles of damage reduced. Right, so this bottom table here is what you're going to use to compare to costs. All right, and with that, I'm done. Questions? I know that was really fast. It was really hard to fit 3 years of work in 1 hour. So yeah, I sped on through that. I got a heavy foot. So I'm sorry, you know, I expect you chew on this stuff. As questions come up, find me on Teams, shoot me an email, give me a call. I have a new phone number. What's my phone number? My phone number is 917-789-4830. Just call me on my cell. We can talk, nerd out. I'm in McHenry County now, so I'm close to y'all. You want to come get me some coffee and talk about FDA, that's cool too. No, I like talking about this stuff. So if and when questions come up, please reach out to me. And with that, I'm done.
Thanks, Richard. I think we had one hand raised. All right. Let's see. Did I see a hand raise from someone?
I think that was me doing the hand clap.
Okay, all right. Thanks, Kurt. Yeah, and that would be very well deserved. So thank you so much, Richard, for giving us an overview. It is a lot to work through. So Richard was, the primary instructor for the most recent. What was the official class called,
209.
Richard?
We're calling it now Introduction to Economic Risk Assessment for Flood Risk Management Studies.
Yes. So I got like a full week of exposure to all this information, and it was wonderful. And I appreciate you condensing it, Richard, to 1 hour and 15 minutes for our consumption. And so again, if anybody has questions, you have Richard's contact information. And we'll just be sure to look out, Richard, for final certification of the model. That said, I will share this recording with fellow MSc economists for their wider distribution across all the divisions. And so with that, thank you so much again, Richard. And thank you all for calling in and preparing yourselves for this future iteration of the model. Thank you.
Dina, if you get me the recording, I'll put it up on my YouTube channel and you can just share the link.
Cool. All right. That sounds great. Thank you, Richard. Thanks, everybody.
My pleasure.